All right, so limits day 4. This, my friends, is the end of chapter 2 in your textbook, right? So we started with chapter 2, except didn't love the way that the textbook broke up limits, so we did it in a slightly different way. Different order. But if you want extra practice problems, going into your textbook is one place that you can find those extra practice problems. And there are other resources out there on the internet as well for you to look up and find other practice problems. But today's going to wrap up our unit on limits. Next week on Monday, we're going to learn one more thing that sort of brings us into why we're looking at limits at all. Okay. And that'll be Monday's content will be the last day of stuff that will be on the first exam. Okay. And that first exam will be on Wednesday, February 23rd. All right. So sort of the closer that we get to exam, the longer this list of what we know gets. Okay. And a lot of them are just the same things we've been talking about, like what is a limit? How do we find limits on a picture? How do we find them algebraically? Right? We talked about this idea of continuity. And on Monday, we took a look at vertical asymptotes and end behaviors. Okay. So one of the things that I think is going to be really valuable as we sort of look into starting to prepare for that first exam is keeping in mind this question of, where should we write it? How do I know when to use what? Okay. How do I know when to use what? And so as you're thinking about it, how do I know when to use factoring? How do I know when to use radicals? How do I know when to just look at the graph? How do I know when I'm looking at a vertical asymptote? How do I know when I'm looking for end behavior, right? If those are all questions that you feel relatively comfortable answering, that's great, right? But if any one of these questions is like, oh, did we learn that? Then I would encourage you to kind of go back into limits day 1, 2, and 3 and see if you can revisit that part, okay? Now the what's new, all right? Well, we wouldn't have a proper introduction to the beautiful world of calculus until we started talking about some theorems and some more formal definitions, okay? So I want to start today's class by forewarning you all that today is a very, very mathematical day, okay? We're gonna even more so than the other days. Every day in here is a mathematical day, but today is even more so mathematical, okay? So well, the first thing we're going to take a look at is something called the squeeze theorem, right? So we're going to take a look at the squeeze theorem, and things that we want to keep in mind is what is the squeeze theorem, and more importantly, how do we use it to evaluate the limit of a function? Right? So in some ways, this might be like, oh, it's another way to think about finding limits. Okay. The second theorem we're going to take a look at is something called the intermediate value theorem. Now, knowing the names of these theorems is also going to be important, okay? So knowing the names, being able to use the same kind of language that we're going to demonstrate here together to show understanding would be really important, okay? The last thing here is maybe one of the most important questions to a mathematician. What is the epsilon delta definition of a limit? And how do we use it to find the limit of a function? So out of curiosity, because I think every group is totally different, are there any math majors out there? Anyone in this room like, I'm going to be a math major? All right. Everyone else is like, no, thank you. I mean, I get it, kind of. I like math, but you know, I'm also a math teacher, so that kind of works that way. But yeah, if you are looking at being a math major in particular, I actually don't know if this course is required for engineering. So this is more of like a very math specific kind of thing. But there is, in fact, an entire course built upon this epsilon delta definition of a limit. And so for those of you who are maybe thinking about taking upper level math classes once you transfer to a four-year institution, you might see this under the name advanced calculus, or sometimes folks call it analysis. Okay. And so just as a heads up for those of you who are like, I'm thinking when I, you know, keep taking the math classes, when I'm all done with the ones I need here, maybe I'll take some more. There is this course on epsilon delta definition. We talk a lot about limits and derivatives that we're going to get to as well, but really looking at like, how did all of this calculus come into play? And we call that advanced calculus or analysis. Okay. So if you're ever curious about what those were, that's what that is. And we'll get a little flavor of that today. But we're going to go ahead and get started with this squeeze theorem. Okay. And so with this squeeze theorem, some folks call it the squeeze theorem, and other folks refer to it more affectionately as the sandwich theorem. Now, I enjoy eating a lot of food. And so for me, the sandwich theorem is like more fun. I like to think about like what kind of sandwiches I'm building. But if we were to think about this theorem right here, I want us to actually look at the theorem first before we give some sort of like fun analogies to them. Okay, so let's take a look at this and read through. So theorem 2.7, this is from your textbook, is called the squeeze theorem. Now it says, let f of x, g of x, and h of x be defined for all x not equal to a over an open interval containing a. If f of x is less than or equal to g of x is less than or equal to h of x, for all x not equal to a in an open interval containing a, and we have that the limit as x approaches a for f of x and h of x equal this capital L, where L is a real number, then the limit as x approaches a of g of x also equals L. That's a lot to throw at you at 9:48 in the morning, right? This is maybe something that we try and avoid, which is like reading our textbook, but it's actually a pretty good skill to have. But I'm wondering if we can sort of unpack why someone else might call this a sandwich theorem. All right, so in a traditional sandwich, how many slices of bread do we have?
Normally 2, but this is a large sandwich.
Okay, so normally 2, right? Let's say that we have 2 slices of bread. Okay, and we think about a filling for this sandwich. Okay, so if you could only put one filling in your sandwich, what would that be? All right, we got a turkey. There we go. We've got a turkey. All right. So let's say for today, maybe we have 2 slices of bread and turkey. I feel like these days for me, it's more like 2 slices of bread and peanut butter because I just have like a very large jar of peanut butter that I'm currently working through. But whatever it is, you choose that filling. Okay. Now, I know I read a lot of this. Let's kind of block that out for right now, because I think sometimes when we look at something that really feels like it has so many words and it's hard to make sense of, we get like a little intimidated. But let's focus rather on this. Okay. You have these three functions, f of x, g of x, h of x. Which functions do you think represent the bread and which ones represent the turkey? All right, we've got f and h is the bread, g is the filling. Yes, I would agree with that. Okay. So in this case, let's kind of consider, how do I want to do this? Okay, let's consider that we have bread. Okay. We have other bread. And we have filling. All right. So we have bread. We have bread. And we have filling. Right. What allowed us to say, I don't maybe know what the rest of this is saying, but I feel pretty confident that f of x and h of x is the bread and g of x is the filling?
Is it the less than or greater than signs that like differentiate the each like bread filling or bread?
Yeah, I would agree that these signs, right? This says that f of x is the smallest one or the lowest one. G of x is in the middle and h of x is on the top, right? So if we think about this like a sandwich, right? We've got on our plate, we have our slice of bread, we have our filling, and then we have our other bread, right? And so these inequalities tell us that the red function is always above the green one, which is always above the purple one, okay? And so the fancy math language here is just saying we've got these functions, but it's not for the entire x-axis. It's not like forever and ever and ever, but it is rather only over an open interval containing a. I'm going to talk about that when we get down to an actual example, okay? But that phrase is important because it doesn't have to be true everywhere. It just has to be true really close to the point we're interested in, okay? Let's take a look at this. What kind of number is L? Yeah, L is a Y value, okay? L is a Y value, right? We've seen it that way in other contexts, but now we're just saying that we have one limit equals this Y value, but so does the other one, okay? This left-hand side, this means that the bottom bread or function gets close to a Y value of L. Whereas this tells us that the top function gets close to a Y value of L. Folks, that's the same as saying you have this sandwich and you just decided to like squeeze down real hard in the middle. Now, this might be a little easier to imagine if we were talking about like a peanut butter sandwich, but it will happen with all sandwiches, like turkey or whatever. If you have bread and turkey and bread, and you squeeze those two pieces of bread together, eventually, if you squeeze hard enough, do your fingers touch?
Yes.
Yes, right? This is saying that essentially the middle part, the filling, becomes one with the bread, and your fingers end up touching when you're squeezing this sandwich, okay? So this middle function, your filling of your sandwich, your peanut butter, your turkey, whatever it is, becomes like an overpressed panini. Like someone smashed it so flat that it was hard to tell, is it bread? Is it turkey? Is it peanut butter? Who knows? Everything was basically just the same. Okay. And that's what this squeeze theorem is really going to be telling us. Okay. So we're going to take a look at a picture, and then we'll kind of come back in and see a little bit more clearly what this open interval containing A means. All right. Now, before I go to the Desmos screen, are there any questions coming up so far? Yes, Nora, go ahead.
So it's not really a question, but I kind of have like a connection. And I don't know if this is right or not, but you know when you take like a hand limit or a right hand limit, and then they both equal like the same exact limit and meet at the same spot, is that basically like the same exact thing?
Sort of, except now we're looking at more than one function. We're looking at 3 functions altogether.
Okay, got it.
Yes, but it is the same idea that like if 2 things on the outside are equal, then the thing in the middle is going to be equal. Okay. All right. By the way, as I'm switching screens over here, I feel like it's probably out of habit that I say, are there any questions? But certainly if there are connections or other examples that are coming to mind for you, or like things you learned in other classes that you think would be helpful to everyone else, you can definitely share those as well. All right. I don't want to limit you to like only questions. That would be very poor teaching. Okay. But for this next part, I wanted us to take a look at these graphs. Okay. So far I have 2 graphs right here. And in fact, I have the x squared and I have the negative x squared. And I hope you can see the negative x squared is in the blue and the x squared is in the red. Okay. Now, I'm going to put in a third function. Okay. And I'm going to have this third function go in between the red one and the blue one. Okay. So knowing that the third function is going to go between these 2, would we call x squared or negative x squared? Which one of those would be our f of x from the notes that we just looked at? Yeah, I would agree. The one on the bottom would be the f of x. So the blue one in this case is the f of x, and the red one is the h of x. Okay. So what happens if I put in x to the third power? All right, now we have a green one coming in here. Now, earlier I said that the g of x, the filling, should always be in between my h of x and my f of x. But if I look here, oops. If I look here, is that green curve always between the blue one and the red one?
No, but right in the middle, it really gets close.
Okay, yeah, in the middle, it gets really close, right? But like down it to the bottom left of the screen, we see that the green one is actually lower than the blue one. And so if we sort of zoom in even more, all right, what would be a good slice? So tell me some x values where I could cut the picture so that in between the ends of this slice, I could see that the green is always between the red and the blue. Yeah,
One.
exactly. Right? So Raylene said that in the chat, -1 right here as an X value. I can see the red is on top of the green, which is on top of the blue. And over here, I can go all the way to +1. The red is on top of the green, which is on top of the blue, right? So when the textbook says open interval, we could say -1. We could say -1 to 1, and that wouldn't mean the point -1 to 1. It means we start at an X value of -1 and we go all the way to an X value of +1. Okay. What do you think would be a good A value? To pick? In other words, where do you think all three graphs have the same Y value? All right.
I would agree too. I think it would be at 0.
Yeah. Okay. Yeah, exactly. Right. At X equals 0, it sure looks pretty hard to tell where each one is, right? And so, oh gosh, I got to stop doing that. We zoom in, we zoom in, we zoom in. Look at how close we're getting. -0.01 and 0.1. And I can't even tell. They all look like they're the same, right? And so that's what all of that fancy language was telling us when we were looking at the squeeze theorem definition from the textbook. It's saying if you have a red graph that is always above a green graph, which is always above a blue graph, but at one point they meet, then all three of those are going to have the same value. Okay. Are there any questions about comments or questions about this picture before we go back to the notes?
Would L equal 0 in this case then?
It would. Yes, it would.
Okay.
Great.
And no, I just wanted to clarify. So like an open interval is the interval where the function g of x is in between f of x and h of x.
That is correct.
Okay, thank you.
Okay. All right. So let's go back to these notes. Oh, yes, Nora, what's up?
So the open interval wouldn't be at 0, it'd be at -1 and 1. X equals -1, x equals 1.
We could say -1 to 1. That would be one thing. We could also say -0.5 to 0.5. So we actually have like a choice in that interval, but you all did a great job of narrowing it down to a place where this is true.
So sorry, 0 sorry, 0 isn't the open interval. Like that's not the same thing, right? I just want to make sure that I'm not getting L confused with the open interval.
So the open interval, all the open, like the interval is from -1 to 1. So we're like cutting a part of the x-axis out. But the open part comes from the fact that we don't actually include the numbers on the end.
Okay.
So for example, open interval, would be like -1 to 1, but a closed interval would be bracket -1 to 1. So it's like the open circle on a graph, where like if you see the open circle, you don't include that value. But if you see like a filled in circle, you do include that value. That's what all we mean by open and closed. Okay. All right, so let's take a look at this definition again, because maybe it was scary the first time. I know it was scary for me the first time, but maybe as we've seen a picture, we can sort of make sense of this a little bit more. So let f of x, g of x, and h of x be defined for all x not equal to a over an open interval containing a. If you have f of x is less than or equal to g of x is less than or equal to h of x, for all x not equal to a in an open interval containing a, and the limit for the bottom function is equal to the limit of the top function at x equals a, then the limit of the middle function also equals L as x goes to a. Okay. There are definitely like video resources out there where people talk a little bit more about the concept of the squeeze theorem, right? So if you're like, I'm not really sure if that makes sense yet, maybe look for a few videos out there and see how other folks are explaining that, right? But I want to also make sure we spend some time thinking about how we do this, okay? And so what we're going to be looking at is constructing the desired inequality. Okay, we want to be constructing the desired inequality. And what I mean by that is we want to come up with a situation where we can find the bread to our filling. Okay, we want to find the bread for the filling that we're given. We want to find it cleverly so that we know the limit of the bread. And because the filling is always between the breads, we'll have our answer that way. Okay. Another way of thinking about it is I sort of have this function that for whatever reason, I can't find a limit for it. But I know the limit of some things around it. So if I know the things around it, right, that's what this line tells us. If I know the things around it, then I can find the limit of the things between it. Okay. So let's see what we can do. We've got the limit as x approaches 0 of x squared cosine of 1 over x. If we were at the very beginning of when we learned how to do limits, we would plug in 0 and see what happens. Okay, so I plug in 0, I get 0 squared times cosine of 1 over 0. All right, what does that give us, folks? All right, I would say 0 squared is 0 times cosine of what's 1 divided by 0? Ah, 1 divided by 0 is not 0, but in fact it is undefined. It is undefined. One over 0, undefined. Okay. And so what's happening is when we plug in 0, we get to a problem. We get to an issue because we cannot take cosine of something that's not even defined. Okay. And so when we see something like this and we look back at the problem, it doesn't look like one we could factor. It doesn't look like there's no radicals. There's no extra fractions in there. So none of the methods that we've used so far would actually be helpful in this case. And so what we're going to do is think about creating or constructing this desired inequality, okay? And so here's where we are going to start. What do we know is true? Okay, what do we know is true? And so one of the things that I'd like us to sort of focus in on is this cosine, all right? Let's do a little brain dump. In the chat, type some things that you know about cosine. What are some things that we know about cosine? I know, but we're gonna have to get back into the trig at some point. So it's okay. It's okay if we don't know yet. It is the x value on the unit circle. It is a trigonometric term. Yes, yes. Okay. One of the most important things about cosine, which does come from the fact that it's an x value on the unit circle, whoops, is this. That cosine of something, okay, cosine of something. I'm gonna write it like this, cosine of theta. What's the smallest value? All right, I like this. Cosine of 0 is 1. Cosine is adjacent over hypotenuse. See, I knew you knew more than you were telling me right off the bat. Tell me about these values though. What's the smallest that cosine can be? What's the biggest that cosine can be? All right, I buy it. Cosine can be as big as 1. Oops. Yes, but it can actually be as small as negative. Okay, so cosine of theta, no matter what theta is, theta can be anything you want it to be. Let me say that one more time. Cosine can be, or theta can be anything you want it to be. But when I cosine that value, it's going to be between -1 and 1 all of the time. Okay. If theta can be anything that I want, and looking at this question, what do we think would be a good thing to call theta? All right, those are good guesses. Those are good guesses. It turns out that all right, so colors are hard. We have theta. I can put anything I want in for theta. In this particular problem, I'm going to put this. Why would I put 1 over x?
Is it because we're working with that problem? So you're just trying to get our brains to just operate no matter what is in that number right there. This is going to be -1 to 1.
Yes, exactly. Because the problem that I want to answer has cosine of 1 over x, if I can call theta anything, let me just call it 1 over x. Okay. Now I start to see a sandwich. I see a filling. I see bread and other bread. Okay. I want to make the filling look exactly like the function I'm given. What do I need to do to make the filling look like the function?
Multiply it by x squared.
Yeah, multiply it by x squared. Now, let me ask you something. We take this filling, we multiply it by x squared. All right, so we have that. What's this? What's this? Nice, nice. Okay. You remember that rule where, like, if you do one thing to one side of the equation, you have to do it to the other side of the equation, right? If you're going to add 2 to one side, you better add 2 to the other side. It's the same story here, except if we're going to multiply this by x squared, we need to multiply everything by x squared. So 1 times x squared will give me x squared on the right, and negative 1 times x squared will give me negative x squared on the left. Okay. And now we have, I cannot remember what colors we use, green, purple, red. Okay. We have bread, bread, and more importantly, filling that matches the question we're trying to answer. Okay. This is my f of x is less than or equal to g of x, which is less than or equal to the h of x, right? Well, the coolest part about the squeeze theorem is I never have to know what the inside is. All I have to know is what's happening to the bread pieces. Okay, so let's check this out. The limit as x approaches, what value should I be trying to get close to here? 0. Okay. So limit as x approaches 0 of negative x squared. And we are choosing x squared because we literally want to match the question. So if this were x to the 10th, I would multiply everything by x to the 10th. Okay. All right, so in the middle, I have the limit as x approaches 0 of x squared cosine of 1 over x. And on the very outside, I have the limit as x approaches 0 of x squared. Okay. So we take the limit everywhere. And what happens when we plug in 0 to that f of x, or the purple function?
Both the bread pieces are going to equal to 0.
Right? I plug in 0, I get negative 0 squared, which is less than this limit that I want. And I think I heard it, that the other limit, when I plug in 0 for x squared, I get 0 squared. And indeed, we get 0 on both sides. And so if both the limits are 0, what's the limit of the filling?
I'm assuming 0 too.
Yeah, it's going to be 0 as well, right? So to answer our question, we would say the limit as x approaches 0 of x squared cosine 1 over x equals 0 by the squeeze theorem. Okay. So the biggest takeaway from this, we should always try substitution like we did before, right? Starting with a mathematical fact, right? Which is usually not a super tricky one, but one that we're like, oh yeah, we did learn that one time. Turns out it's useful for some other things too. And then we sort of construct the desired inequality. And all we mean by construct is that ultimately we want to make the thing we started with look like the question we're trying to answer. Okay, we want to take the thing we started with and try and make it or construct it to be the same as the question. All right. All right, so I see a question in the chat. Is the typical math fact the range of the filling function? It can be, yeah. The range is a good place to start because the limits are all going to be y values. So if you can sort of sandwich that in between two other y values, then that's a great place to start. All right, let's try example 2, all right, which is pretty similar to example 1, all right? And so for example 2, we see this question, we're like, oh, Judy said we should always try substitution first. We get 0 times sine of, whoops, undefined, because we're like, oh yeah, we talk about that a lot. 1 over 0 is undefined, right? And so that's a problem point for us. And then we look back at the question and we're like, run through that checklist. Can we use factoring? Can we use radicals? Can we use complex fractions? Nope. Looks like a classic case of squeeze theorem. Okay. And so let's start with our what do we know is true? Oops. All right. And what would you say might be a parallel statement that we could make for example 2?
Do we have to go back and figure out like what sine could be and what?
Yeah, that's a great thing. Okay. Now, it turns out that cosine is the x values on the unit circle, and sine is the y values on the unit. Okay. It turns out sine and cosine, yes, have the same range, meaning from -1 to 1. Okay. So we can say -1 is less than or equal to sine of theta, just less than or equal to +1. Right? What could we do next in our goal of constructing something that looks like the original question?
Just take -x to the 4th. Basically follow the same steps that we did above.
Okay, so I see that multiply by the x to the 4th, but before that, we want to replace that theta. Okay, so nice catch, Dan. We want to replace that theta. What would be a good choice to replace that theta? 1 over x, right? And we're choosing 1 over x. Oops, we're choosing 1 over x because that's what happens to be in here. And we want that to be our theta, right? So we're going to make 1 over x. But if this were 1 over x squared, I would put 1 over x squared, right? Or if this was 1 over x to the 10th, I would put 1 over x to the 10th. So it's all about matching the question, not just like using the same method all the time, okay? All right, now I think we can multiply by that x to the 4th. And so we'll get negative x to the 4th, x to the 4th, sine of 1 over x, less than or equal to positive x to the 4th. All right, what comes next? Before we substitute, isn't there an issue with negative x to the 4th? What do you mean by that?
So essentially, like number you put into the negative x to the 4th and the x to the 4th, it's the same thing. So isn't it not squeezing it by pretty much being the same function?
Ah, okay. Well, so you see we have the less than sign, but we also have a less than or equal to. So it's actually okay if the two ends of the bread are the same. They
Okay,
give us
thank
the same
you.
value. That's actually what we want. We want the two to be the same at the x value we plug in. All right. But before we substitute, we got to apply the limit. All right. So we actually have to write that out, applying the limit, and then we can substitute. Write that out. Right. Now we can try substitution again. We should get 0 is squeezing from both sides. So in other words, our capital L that we saw on the other page is 0. And so we finish off by saying something like this. The limit as x approaches 0 of the thing we want is 0 by the squeeze theorem. Okay, so we want to make sure that we finish answering the question. Limit as x approaches 0 of x to the 4th, sine of 1 over x equals 0 by the squeeze, or you could write sandwich theorem. Okay. So I don't think I was kidding around when I said we were going to do, like, today was a very, very mathematical day, right? We're thinking about constructing things. We're going back into the recesses of our brain and trying to remember some things about trig. We're thinking about this very abstract concept, right? Where if we have two limits that are the same, and then there's a third function that's always between the other one, it ends up having the same value. That's just another technique to find a limit, okay? I would say for example 3, okay, if you are looking for, this tells you a y, limit as x approaches 0 of sine x over x is 1, using the squeeze theorem. But I would say if you are pretty good with just knowing example 1 and 2 and like how we work through that, that would be way more important, okay? Example 3, I think, is an interesting proof for those of you who are thinking about diving more deeply into mathematics. I think example 3 is worth looking at, but I would say that short of being the math major, it's maybe not as important for other folks in the classroom, okay? All right, so it is 10:30 right now, which seems like a great time to take a break. So let's be back at 10:40, all right? And then when we come back, we're going to be taking a look at something called the intermediate value theorem, okay? And then after that, we will finish off with our epsilon delta, which is the mathiest of all math things that we will take a look at today. And I'll see you folks back here in about 10 minutes. All right, so before break, we talked about the squeeze theorem, or also known as the sandwich theorem, right? Whatever helps your brain understand that concept a little bit better, what connects better to you is fine. And now we're going to talk about something called the intermediate value theorem. And we're going to try a reverse strategy. So I've included the theorem from your textbook, so you can take a look at the formal language, but this time we're going to start with the example, and then we're going to go back and look at the theorem, okay? And so I wanted to kind of showcase both ways of doing things, because I think that sometimes as we're reading textbooks, we start with the stuff first, and then we're like, I don't know. And then we get to the question, we just feel like discouraged. We don't know what's going on. And so even if it was a question we were able to answer, we maybe feel less confident about it. Okay. So blah, big scary thing, but like, let's look at an example before we really get too caught up in the big and scary. Okay. So, all right, let's take a look at example 4. If f of 1 equals 2 and f of 3 equals -7, stop right there, okay? If f of 1 equals 2 and f of 3 equals -7, can we draw a picture of just that first part of the information? Someone tell me how I could draw a picture for the first part of the information.
You could just draw 2 points on a graph.
Great. What are the 2 points?
1, 2, and then 3, -7.
Great. 1, 2, 3, -7. Precisely. Okay. So this will very much not be to scale because I'm squeezing in a tiny picture right here. All right, but all right, so we've got our x-axis, our y-axis, and let's say that we have 1, 2, and we have 3, -7. Okay. In fact, let's maybe color them just to make sure we know this one is the same as this one, which is the same as this point. And go big bird themed. 3, -7 is the same as f of 3 equals -7. And that's this point down here. Okay. And so because I used the F notation, it means that I have a function that connects the yellow dot to the orange dot. Okay. Are folks able to annotate on my screen? I know that can be hit or miss sometimes, but is anybody able to annotate on the screen? It's like the high-tech way of coming up and writing your work on the board. It's okay if it's not working.
I think you need to enable it. Like you need to do it. I think.
Advanced sharing options. Huh. Okay, so if I go to view option. Oh yeah, it doesn't have that as an option here, huh? Okay, well, that's a problem that I can think about a different time. Okay, so if I were to connect the yellow point to the orange point, what's one way that I would do that?
Draw a line.
Yeah, draw a line, right? Short and simple, draw a line, okay? What else could I do? A curve, yeah, maybe it looks something like this. That's valid. Maybe it looks something like this. That could be crazy and wacky, right? Maybe it goes like this. Lots of different choices. But all of those choices had one very specific thing happen, okay? Every single one that I drew, I had to cross the x-axis, right? If I did a straight line, cross the x-axis. If I did like a curve, cross the x-axis. If I did a curve the other way, cross the x-axis. If I did that crazier one where I went up and then I came down, cross the x-axis. Every single possible way that I could connect 1, 2 to 3, -7, I have to cross the x-axis. Now let's read the second part of the sentence. What is one possible value of f of 2? So we have 1 here. We have 3 here. F of 2, well, at 2 is right in the middle of 1 and 3. It might not happen, but it's possible that I get a 0. Okay. And the reason why we can say that is true is because in order to get from the yellow to the orange, at some point we cross this line. Okay. And so we could say something like this. F of 2 could equal 0 since we must cross the x-axis to go from 1, 2 to 3, -7. Okay,
May I ask a question?
for sure.
Can we also write, since it is one possible value, could we say anything between 1 and 3? Since it's going to cross the x value at any given.
Oh, like if I change the question to say f of like 1.5, you mean?
Oh, actually, I just answered my question when you did that 1.5. We're looking at 2. Sorry. I was thinking like it could be any value between 1 and 3, but we're only focusing on 2.
Yes, it could be any value between 1 and 3. And so, yeah, that's actually exactly the point. This is 2. 2 is less important than the fact that it is between 1 and 3.
Okay.
Okay. So the fact that it's exactly halfway between is less important than the fact that 2 is between 1 and 3. So Enrique, you're right. We could do 1.5. We could say 2.5. We could say 2.99. Any x value between 1 and 3 could have a y value of 0 because we have to cross the x-axis to get from one to the other.
Okay. Yeah,
It's a
thank
really
you.
great question. Nice. Okay. All right. Let's try example 5. Okay. So slightly differently worded. It says show that f of x equals x cubed minus x squared minus 3x minus 1 has a 0 over the, check this out, brackets. So I would say closed interval 0 to 1. Okay. Now, over here, what Enrique just pointed out, the 1 and 3, that's the closed interval for example 4. So the X values are the closed, they tell you where the closed interval starts and stops. Okay. Well, I don't know what the graph of this looks like off the top of my head. I know that it's X cubed, and so it probably looks something like this, but I don't know where it crosses the X-axis. And remember from the other day, we said that a 0, and maybe we'll write this in, a 0 is the same thing as an X-intercept, right? So it's almost like a little twist on example 4. We're asking for the same thing, but we're changing how we get that information. So if I have an X value of 0, right, that would be like my F of 1. How would I find the Y value that goes with 0? Plug in 0. Perfect. So let's do that. All right. I'm going to find F of 0. And so I get 0 cubed minus 0 squared minus 3 times 0 minus 1. Let's be really careful here. We get 0 minus 0 minus 3 times 0 is 0 minus 1, which gives us negative 1. Okay. And so this really means that, I should have left myself a little bit more space. This really means that the coordinate we're looking at is 0, comma, negative 1. Okay. All right. What other number should we plug into the function? Great. And 1 is because that's the other end of the closed interval, right? 1 is like our 3. So let me plug it. Oh, let me plug in 1, not 3. And I get 1 cubed minus 1 squared minus 3 times 1 minus 1. Let's see, 1 minus 1 minus 3 minus 1 gives us negative 4. Yeah, mental math can be hard sometimes. I think it's negative 4. And this would be 1, comma, negative. All right.
I
If
think
I
what I'm
were-
confused on is the interval. Like if I thought that was X and Y.
Oh,
Sorry to like over talk over you, whoever was talking. I'm so sorry about that.
yeah.
I got really confused right now, but then I was like, oh, the brackets.
Yes, yes. It is tough also because, and I'll sort of squeeze this in up here. Like if I write A comma B, this means the open interval from X equals A to X equals B. And I know that looks like a coordinate point. And so that would be one of the things, like as you're sort of reading through a problem, if you can look at the word interval, if you see interval, likely this is not a point. Yes, Dallas, what's up?
I had a question about you said that we were finding the x-intercept, but we just plugged in 0. Isn't that finding the y-intercept?
Ah, okay. So it would be, let's make sure we know why we're plugging in what we're plugging in. So like this 0 is the value we plug in because we're looking for like the y value at that point.
But doesn't the interval say that we can't use 0 because isn't the square non-inclusive?
Square braces means we are including it.
Oh, okay, that's right.
Yeah. And then that's why like we could plug in the 1 over here for that.
So to piggyback, we did find the y value, -1 and -4 would be our y values.
Yes. Yes.
Okay.
Okay.
Now I'm back on track.
Yes. Excellent. All right, Nora, what's up? Thank you for being patient.
Yeah, no worries. So in simpler terms, is this basically asking between the x values 0 and 1, where does the x, what number in between there hits the x value at 0? What y value? Do you know what I mean? Does that make sense? Like in simpler terms.
I do, yeah. So I think like if we look at example 4, you would be saying between the x values of 1 and 3, we are guaranteed to find a y value of 0.
Yes, exactly. That's what. So you know you're gonna hit the x-axis. It's just basically asking where you're gonna hit it.
No, we don't even know where. Sometimes we don't know where. We just know that it happens.
Okay, but then when we plugged in 0, you know how we got 0, -1? Wouldn't that be our answer? Like that's where it hits the x-axis.
Ah, okay. So 2 quick things. Let me make one small correction. I believe this is actually supposed to be a +1. That's going to change this to be a +1. And I think this changes to a -2. But when we're looking at an x-intercept is when the y value is 0. So like this is not an x-intercept.
Yeah. Okay, that makes sense.
Okay, but let's throw it on a graph, right? Because it's completely understandable that we're like, well, it's hard to keep track of what we're looking for. But when we say we're looking for a 0, we're secretly saying, where does it cross the x-axis? So if we graph this 2 points that we have 0, 1, and then 1, -2. Right? And so between this point and this point, an x value of 0 and an x value of 1, somewhere in between there, we have to cross the x-axis. So that guarantees that we have an x-intercept between the x values of 0 and 1.
Okay, that makes way more sense because I was actually agreeing with Nora that I was like, okay, that should be our answer, but like visually, I see what you mean. It could cross at any point between those.
Right.
Yeah.
Yeah.
Thank you for clarifying.
Of course. The question is there. Oh, okay. You got it. Great. Thanks, Dan. Okay. So let's do one more example. Okay. And then we'll go back and look at this definition. So example 6 says that I claim that the function 1 over x does not have a 0 over the interval. So these are both x values from -1 to 1. This, by the way, is very equivalent to how I take notes for like classes that I'm taking. Like if the instructor provides notes or if things are said out loud that aren't necessarily written down, like I'll write them out myself just because sometimes I'm like, I can't remember what this notation means. I can't remember what that notation means. But as I start to like write them down, it helps me remember them. And then I also can go back and read it myself later. Okay. So these are both x values. And when I plug in the x values into the function, f of -1 gives me -1 and f of 1 gives me 1. So if we were to sort of imagine just plotting those points right now, x, y, and we have one point that is -1, -1, and the other point that is 1, 1. based off of what we've been talking about, if I were to connect those 2 points, wouldn't I have to cross the x-axis at some point?
Yes.
Yeah, we should, right? There's no way to connect those 2 points without crossing the x-axis at least one time. Okay, and so this is something important that we're going to see in our definition, but I wanted to make sure that we could see it actually before we see it in the definition. So it goes back to this function, okay? F of x equals 1 over x is a nice function to know. If you were in my class last semester, I was like, you should probably know this graph, right? One branch looks like this. The other branch kind of looks like this. And as Dallas says, it's a rational function, right? In fact, so this is like our orange point. This is our yellow point. So in fact, we have a vertical asymptote here. Okay, and if you didn't remember there was a vertical asymptote, you could also use Rayleigh's method, which is 1 over x. If we literally plug in 0, we're going to get undefined. Okay, so the fact that this graph, the only way to draw it is to pick up my stylus and start again on the other side, means I have a discontinuity at x equals 0. That means that in the interval I'm looking at, I have a discontinuity. And if I have a discontinuity, then I'm no longer guaranteed to be able to connect them and therefore guarantee the x-intercept. Okay, so that's kind of a lot. Let me write that out. Because 1 over x has a vertical discontinuity in the desired interval, -1 to 1, the intermediate value theorem does not. Okay, so that would be a very clear way of saying that, in fact, we have to have only continuous functions to apply this theorem. In other words, the assumption in example 4 and 5 was that these were both continuous functions. Okay. So the gist of this theorem is going to be that if something is continuous, if a function is continuous, we can guarantee that we achieve certain values. But if a function is not continuous, we're not necessarily guaranteed. Okay. Yes, Dallas, what's up?
I think what you just said just kind of cleared it up. But so essentially for 4 and 5, we weren't necessarily trying to find like the actual x-intercept. We were just trying to tell if it was continuous from point A to point B.
We were actually assuming that these were continuous. So if I had done a better job writing these questions, I would have stated that the functions were continuous.
Okay.
Okay. So to be more clear, I would say, given f of x is continuous and we have these, what is one possible value of f of x? And the fact that I tell you it's continuous in the beginning means, oh, you can draw a picture. Does it look like we have to cross the line? Yes, it does. Then we're guaranteed to get a 0 out at some point.
Yeah, because I was thinking like we don't know what f of x is. It could be like a piece or something and actually not have a value.
Great,
But that makes
exactly.
sense.
Okay, great. And that's actually one thing you'll find in textbooks. Sometimes they leave out that information, but we can tell from example 6 that like discontinuity is actually a big deal, right? So that's a great catch on your part. Yes, Alexis, what's up?
On the note that you wrote, so it says the blank value. I don't know what that word says.
Oh, intermediate.
Oh,
Yes.
thank you. Sorry about that.
Not at all. Please do clarify. And especially like remote or when we're back in the classroom, my handwriting can definitely get out of control with like my loopy situations. So please do ask. Never feel bad if you can't read what I'm writing. That would be so terrible if my handwriting was terrible and then I was like, I don't know, fix it, figure it out, like you figure it out. Okay, so all of these 3 examples are meant to help us understand this intermediate value theorem, okay? So let's go back now and read what the textbook has to say before they let you do any examples. And so you can see here, they say, let f be continuous. All right. So as I were reading this, I would even highlight that because I'm like, well, we just did a few examples, excuse me, and continuous was kind of a big deal, right? Even though it's only the 4th word in, it's kind of a big deal. So let f be continuous over a closed bounded interval a to b. And I might even write here, if it's not fully stuck in my brain yet, a and b are x values. So when I see that, I want to be thinking that they're x values. And I want brackets because I want to be able to include them. And the word bounded just means no like infinity or negative infinity in the brackets. That's all that means. Okay. Alexis, did you have another question?
Oh no, I forgot to take my hand down. Sorry.
Oh, okay. Yeah. So when you raise your hand, do you have to put it back down? Is that how that works?
Yeah, I think
Okay.
so.
Okay, cool. Thanks. I feel like I should know that by this point, and I don't. Okay, so if z is any real number between f of a and f of b, all right? So maybe I shouldn't have used yellow over here. Maybe I should have used like green. Which kind of looks yellow. But f of a is like the yellow point that you drew in the pictures below. F of b is like the orange points that we drew. Okay. This is my f of b. This is my f of a. All right. It says if z is any real number, what kind of number is z? Is it an x number or a y number?
I would say X or Y.
Ah, it's hard to tell, right? Because I don't know, this has like f of something. Wouldn't be this be f of something? But one way that we could tell is take a look at the picture. Sometimes the pictures they draw are labeled way better than the way they're describing it in words. And so if we look at the picture, maybe we can tell that z is a y value. Okay.
I think it's because we keep talking about crossing the x-axis. I'm like, oh, it's like the x.
I know. And reading math in general is just hard. It's hard. Right? But if we have a y value that is between f of a and f of b, then there is a number c in the interval a to b. So what kind of number is c? Yeah, that one's an x value. And we can see that c is, we can see the c on the x-axis. Okay. So there is a number c in this interval a and b. All right. So this is what Enrique was saying earlier. If this was our 1 and this was our 3, we could choose any number in between 1 and 3. this is the mathematical way of saying exactly what he said earlier. The number C is in the interval A to B, meaning it's between A and B. It's not alphabetical, okay? But the cool thing about this point is that C will give you the Y value you want, okay? So let me get this all on one page for a sec. All right, how are we feeling about this intermediate value theorem?
In some weird way, I find this way more easier than what we just learned on day 3.
All right, all right. Maybe it means you are much more of a mathematician than you think you are. All right, so we've talked about the squeeze theorem, all right? We've talked about the intermediate value theorem, and I'm gonna give us a little bit of a break before we talk about the epsilon delta definition, okay? Now, I will, before we go into the epsilon delta definition, I do want us to, when we study these examples, study the ones that look like what we're getting in class, okay? If you start Googling epsilon delta, there is a rabbit hole of a lot of math that will pop up, which is fine. And you are welcome to try any of those that are more challenging. But for the context of this course, I really want us to just get a good grasp on the most fundamental application of the epsilon delta definition of the limit, because we already have so many other tools to look at limits, and unless you're going to be a math major, it might not be as important to the trajectory of your career. Okay, and I want to respect the fact that even though I love math, maybe we're not all going to be math majors, and that's going to be okay. All right, so it is 11:12 right now, and I'm going to say let's be back at 11:20. All right, I know this has been a lot of dense conceptual stuff, so let's be back at 11:20 today, and we'll finish off class with this epsilon delta definition of the limit. All right, so the last big concept for the day is something called the epsilon delta definition of the limit. And so congratulations, you have reached a point in your math career where now there's not enough letters in the English alphabet. And now we use Greek letters too, okay? And so who knew that taking math meant that you were also going to get to learn Greek letters and how to write them? And so we have our epsilon. Let's see, let's go with yellow. And so I'll just write a few epsilons up here, but these little curly E things, these are what epsilon sort of print out when you're like typing. But when you're really writing them by hand, they sort of look like a little roundy E like that, right? So you could just sort of practice a few, but that is how we write epsilon. And the delta part, this one is, I think, a little bit trickier to write, but it looks like a sort of scripty D, all right? So D like delta. And this one, I usually start at the top. So I start at the top and then I come down and then curl it around like that. Okay, wonderful. I learn something new every time. Thanks for sharing. All right, so we've got epsilon, we've got delta, and I will tell you right here, yeah, it's kind of like a musical note. So I would say like a musical note's more like this, right? But it's a little bit curlier on this part, right? So it sort of goes in and then comes back out, but it's exactly like that, okay? All right, so epsilon delta definition. we're gonna start with our definition. We are going to figure out sort of a like what the storyline is, and then we are going to take a look at some examples. All right. So we will come back to this part if we have some time at the end. Again, there are some of us who were maybe planning to continue a little bit further into mathematics, and so starting to learn some of the notation that we'll use later, not in this class, but like in future math classes, kind of is like a fun thing to do, okay? So our definition, this says, let f of x be defined for all x not equal to a, all right, over an open interval containing a. So we're going to have some sort of open interval where we'll have like an x value and then another x value. And somewhere in between those two x values is going to be a, and a is also an x value. Okay. Let L be a real number. So we're going to focus on real numbers in the context of this course. Okay. Then, and hopefully this looks familiar, we saw this on the very first day, the limit as x approaches a of f of x equals 0. Oh, L equals L. But this is only true if for every epsilon greater than 0. So we're going to have some epsilons that we're going to assume are positive. There exists a delta, which is also positive, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Let's come back to this definition after we've sort of looked at a couple pictures and kind of talked about the concept, all right? So we'll sort of blend the two techniques we tried earlier, right? For the squeeze theorem, we read the definition first, we really dug into the definition, then we looked at a picture, and then we looked at the questions. And then for the intermediate value theorem, we did examples first, and then we went back to look at the definition. And so this time we're doing a one-time read of the definition. We're going to go ahead and look at some pictures and then come back to the definition and see if that makes a little bit more sense. Okay. So trying to model a bunch of different ways for you to access content. All right. So in case you can't tell by now, I love pictures. Pictures help me understand math in a way that can be harder for me if I only have algebra, I only have a number, or I only have equations. And so let's take a look at just this first picture. Okay, just this first picture. So the idea here is that we have some value of x, and if we put x into a function, then what comes out is f of x, right? So if I put x into a function, so input x into a function gives output of f of x. And so if I think about if I input a into a function, well, we hope that that output is f of a. Okay. So this graph or this graphic is more about sort of the input and output relationship that we see with functions. Okay, that's kind of weird. All right, now let's look at this middle picture. Okay, so the middle picture is a little bit different, but we're still saying that in general, if we put x in, we're going to get f of x out. Okay, but imagine instead of just taking a, you took a whole group of a's, like there were a lot of different points in here. And you took all of them and you put them into the function one at a time. Well, the output would give you a lot of different outputs. Instead of just one output, you would get a lot, one for every single point that you ported over. Okay. This is like taking an interval of x values and bringing them over to an interval of y values. Okay, so we're going to take intervals of the x's and sort of port them over to intervals of the y. Right, so this is sort of like a very mathematical thing. But let's maybe bring this back to something that perhaps we can all relate to. So I know I haven't met you all yet in person, but the very fact that you are signed up for a class, a Calculus 1 class, a 5-credit class, and that, you know, you are doing the things necessary, like attending class, things like that. Like, I don't think anyone signs up for this class and is like, I'm going to try and fail this class on purpose by not doing my work. Like, I don't think that anyone brings that mindset into the class, right? But I'm wondering, like, what are some goals that you all have to get out of this class? Maybe just put a few in the chat. What are some goals you have for yourself for Math 150? Great, I love these. I love these. We want to get good at the content. You want to understand what's happening, prepare for future courses, learn how to ask questions, be able to apply it, advance to the next part confident. That's a huge one. I don't think I do my job. If you do well in this class, but then you find the next class super hard, then I don't feel like I did my job fully. I want this to be something that pays off for us in the future as well. Challenge myself in a topic I've always been afraid of, pass with a certain grade that we're trying to get and actually grasp the concept. Complex differentials. Yes, get rid of the anxiety I get when I think of math. I love these, such great goals. Okay, now understand it well enough so I can explain it and not be scared of seeing questions. Love it, love it. Even more complex math. Wonderful, wonderful. All right. So if you shared in the chat, awesome. If you didn't, whatever your personal goal is, just kind of think about that. Okay. And so here's the deal. Here's how this ties into this weird looking picture we have here. I think we all have a range of like what's acceptable for us, right? I saw someone in particular who said, I want to pass this class with a B or better. So like maybe this is a B and an A grades, right? Everything in here would be the output you're getting A's and B's. Okay. Or let's choose a different goal, right? You want to actually understand that concept and be able to ask questions. So if you feel like you're able to ask questions or you really get the concept, you can explain it to someone else, that means you're right here in this zone. Okay, so this is the zone where you're like, yes, I have reached my goals. Okay. This is the output. This is what people see. They look at your transcript, they're like, A in Calc 1, 4.0, 5 credits, that's awesome. Or they look at you in the next class and they're like, wow, this student really gets what we're doing. It's clear they had a very solid understanding from Calc 1. Or you know you're in this zone when you're like, I just asked some really good questions. Okay. Those are all outputs though, things that people see, things that you see. What we don't always see, what we don't always talk about is literally the input. What do you have to do? What inputs do you need into your system so that you get into the region where you're achieving your goals? Okay, that's literally what the epsilon delta definition of the limit is saying about limits. All right, it's basically saying if you want to achieve certain goals, okay, in this case, the goals are y values. You want to get to certain y values, right? So maybe the y values is like your grade, right? If you get that 80% or higher, you know you reached that goal. Whereas this part down here is things that need to happen to guarantee your goal. Okay. Things that need to happen are the input so that you can achieve your goal. All right. I won't make you share this part, but for whatever goal you set forth right here, think about what are those things that need to happen to guarantee that goal, right? For some of us, maybe it's like, if I want to challenge myself to ask more questions, ask better questions, then I actually have to ask questions, even if I think it's a bad question, right? And so as time moves forward, we get better and better at finding a collection of things that when we do these things, we get the output that we want. Okay. All of this, though, is dressed up in this math language, right? So what I want you to think about is when we talk about the epsilon part, the epsilons are like, let's say your goal is to get a 90, right? A 90% in the class. Well, maybe if you get some 100s and some 80s, it'll average out to a 90. But all of that is still within your goal sort of frame, okay? So epsilons are like, how acceptable is your output? So if you are taking this class at Mesa, which we all are, right? At Mesa, we actually don't have pluses and minuses. So we don't have plus, minus on transcripts. What this means is an A minus weighs the same amount as an A plus on your GPA. Okay, so I think a lot of us are looking to transfer. It would be worth your while to get to that A minus because it's going to count as a 4.0, whereas a B plus weighs the same amount as a B minus. Okay, so think about it like, what's your acceptable range, right? What's that acceptable range for your output? And in order to do that, you might have to have a certain definition of the things that you're going to do to guarantee that goal, right? Maybe it's not that you ask a question every single day and you go to every single office hours and you go to every single tutoring. Like that seems unreasonable. So maybe you give a little bit more on some days, like a little plus delta, And maybe other days you're like, you know what, I was working late last night. I'm just tired today. My brain's not in it. Maybe that day's a little bit less. But at the end of the day, you're still pretty close to an input that'll get you the output that you want. Okay. So my attempt at trying to make this relatable, let's go back to the definition and see if this is making any sort of sense. Right? So we have this definition, right? We're thinking about a function. It's defined over some open interval. Those are all x values. And inside that interval, there's something that is an input that we're really looking to do, okay? But around that input, maybe some days it's a little bit more, some days it's a little bit less, but it sort of ends up being around A, okay? So we have an input of A. And if we input as close to A as possible, we're gonna get an output that we really want, all right? The epsilon here is like a little bandwidth to say, maybe I wanted the 90, but maybe an 85 one day and a 95 a different day still gets me to the same point. And it's okay to not be perfect all the time. Okay. That's what we're really doing when we're trying to prove formally that we can find a limit. All right. So let me pause here for a moment. We're gonna take a look at some questions in a little bit, but do we have any questions, comments, concerns before we take a look at an example? Okay, good. That's the goal. That's the hope. Okay, so what does all of this look like? All right. So the questions are going to look something like this. And so in particular, when we see the word, let's go bolder. When we see this word prove in our brains, in our class, we want that to say, oh, Judy means use the epsilon delta definition. Okay. So when you see the word prove, you want to think, oh, we got to use the epsilon delta definition, which is the process that we're going to do right now. Okay. And so I like to break this down into 3 parts. Okay. So we're going to write this out for every single one. All right. We're going to start by saying given epsilon greater than 0, we choose delta to equal, and we're going to leave a blank line. Okay. At the end, we're going to put our answer here. This answer goes here. Okay. So given an epsilon greater than 0, choose delta to be something. And we'll leave that alone for right now. Now we're going to suppose that 0 is less than x minus a, an absolute value, which is less than delta. Now I got that from the definition above, okay? And what we're gonna do is everywhere we see the a, we're gonna put the number that we want the x to get close to. So in our example, we're gonna say 0 is less than the absolute value of x minus 2, which is less than delta. 3. We're going to choose the following. Absolute value of f of x minus L, close the absolute value, is less than epsilon. From our example, what can I plug in for L?
6.
Yeah, 6, right? That's our limit. All right. From our example, what can I plug in for f of x?
2. No, sorry.
2 would be the a value, but we are indeed going to do as Raylene suggested. We're going to plug in this. This is our function. 5x minus 4. So this gives us 5x minus 4 minus 6. And we're going to leave that less than epsilon. Okay. Here's what's going to happen. We're going to simplify this so that we match it to what we found in step 2. Okay. 5x minus 4 minus 6, I can rewrite that as 5x minus 10. Everyone buy that? You could have it say 5x minus 10 instead of 5x minus 4 minus 6. What's the greatest common factor for 5x minus 10? Great. All right, so we're going to factor that 5, and then what's left?
X minus 2.
Like that? It is exactly like that. Okay. All right. Now, let me ask you sort of a side question. Is this equal to this? Yeah, it is indeed equal. So if we have a number in here, okay, that's multiplied by a bunch of other stuff, we can take that constant out to the front, all right? How might we apply this on this line?
Just remove the 5 to be outside the absolute value.
Great. All right. Now I said earlier, it would be really nice if we could get something that looked like this. And moreover, can we get something like that all by itself on one side? The very fact that you factored out and you got that x minus 2 is such a good sign. We were able to bring the 5 out to the front, but now how do we isolate this?
Divide the equation by 5.
Perfect. So absolute value of x minus 2 is less than epsilon over 5. Okay. Now, check this out. Here's the 2 from earlier. Here's this 2 in step 3. Okay. Here's the delta that we had, running out of colors. Colors are hard. And look what we got. Epsilon over 5. Okay. What this means, we're now going back to 1. So given any epsilon greater than 0, if we let delta equal epsilon over 5, then this limit will be true. Okay. Now, how does that relate to the analogy that I was trying to give about your goals and like as your output and the things that you do? What this means is that this is sort of the amount of wiggle room you give yourself to say, some days I can get it, you know, I'll go to like office hours, but other days maybe I'm going to sleep in because I didn't get any sleep last night and I'm going to be tired during class if I don't sleep more. So it's like the give and take. If you give and take this amount, you're still going to get really close to an output of 6, or you're really going to get close to being able to meet your goals. That's all this is helping us find. Okay. I know this is a lot in terms of the process, and we have about 10 minutes left. And so I think what I'd like to do is do example number 9 to kind of give us a little bit more practice with this process. So we could go through it at least one more time. Does that sound good to folks? Okay, cool. So we're going to go to example 9, all right? And we see again that we have our, whoops, prove that this limit is true. And so we're like, oh, that's right. This is the epsilon delta definition. Okay. And so knowing it's the epsilon delta definition, we have sort of those 3 steps to follow. Okay. We're always going to start with the same sentence given epsilon is greater than 0. And you can think about that saying like, given that you're not going to meet your goal every single time, but you're going to get pretty close to it, choose delta to equal, and this is where your answer goes. Okay. The answer means how much do you have, how much wiggle room do you have in your input to still get the output you want? So then we're going to suppose that 0 is less than absolute value of x minus a is less than delta. What's the a value in this question?
-1.
Good. It is in fact -1. So I'm going to be really careful about that in my brain. So careful that I'm going to actually change it to x plus 1. Now, no matter how much work I do in the next step, at some point in the next step, I'm trying to make an x plus 1 pop out. Okay. So next, we choose the following. We want f of x minus L is less than epsilon. What can we fill in for our L?
-3.
Yeah, so this is going to be our L, -3. Well, better be careful about that sign as well. And then my f of x, what do we put in for our f of x? Great, 4x plus 1. Okay. Now we're very careful with our arithmetic. We get 4x plus 1 minus -3 is plus 4. which is less than epsilon. What can I do from here?
Factor out the 4, so then x plus 1 shows up.
Bingo. Now I want to match this entirely. And so we have that if we want to be pretty close to a certain output, we can be a little bit less than perfect by epsilon over 4 in both directions. So maybe some days it's a little bit more effort, some days it's a little bit less, but either way, anything within this range of inputs will get us to the -3 that we want, or whatever goal it is that we want. Okay. All right. And actually, we have a little bit more time. I want to do example 8 just to show you that it doesn't work all the time, and it's okay if it's not going to work all the time. But in this case, we have proved that that limit doesn't equal, it doesn't equal 3. Okay. So given epsilon greater than 0, right, we choose delta to equal something, right? And so if we suppose that 0 is less than the absolute value of x minus a, which is less than delta, what would we put in for the a value here? Great, a is 2. All right, now choose the following. So what's my f of x in this case?
(5x minus 4).
Good, so f of x minus the L, which is 3, should be equal to epsilon, right? If we were proving that it was equal, we would want to show that it's going to get to 3. And so if I combine these, I get 5x minus 7, which is less than infinity. And if I were to factor out a 5, I would end up with x minus 7/5, which is not the same as x minus 2. Okay. So since these two do not match, we can say that the limit as x approaches 2 of 5x minus 4 is not equal to 3. All right. This style of argument is sometimes called proof by contradiction, right? So we'll say like, well, if we want to show that something is true, we assume, what if it's not? And then we show that, oh, that can't happen, so it has to be true. Okay. But I think for the quiz for this week, I believe that example 7 and example 9 will be really helpful in those formal definition, prove with the epsilon delta definition kind of questions. Okay. And so we have made it to the end of limits day 4. How are we feeling, folks? 2 weeks in and you're still there? All right.
This was actually my favorite day.
I love it. Maybe we now have more potential math major converts. Yes. All right. Well, my friends, that is it for today. So if you have any questions, you're welcome to hang around for a little bit. Otherwise, there is tutoring tomorrow and Friday, no, tutoring Friday. And so you can go and work through the quiz questions with Ethan. And you can always ask questions on Discord or hop on the voice channel and work on stuff together. So don't forget about all of that, okay? And I will see you folks on Monday.